So recurrent neural nets, you might not know, but was one of my first loves. During my PhD, I worked on recurrent nets and I worked on sequences, and I got very excited about them. And then as I played more with recurrent nets, I realized there was something wrong. That I was trying to learn some things and they didn't want to learn them, and I was frustrated. And I tried to figure out why. And that's how I came to publish this work that I'll tell you about regarding the difficulty for recurrent nets to learn long-term dependencies and everything we've learned about how information propagates through recurrent nets. Some of it applies also to the difficulty of training deep nets in general. So hopefully you'll come out of this lecture with more understanding of recurrent nets, but also of some issues that apply to other kinds of deep learning. So people draw pictures for recurrent nets in two different ways. So what you see on the left is the kind of drawing that people used to draw in the 80s and 90s, where people were thinking about circuits and neurons. So the little black square here means that there's a delay in the connection from the state at some time to its next value. In other words, the units are connected to each other, but through a delay. And so what we can do to better understand what is going on, what is the computation that's happening, and also to implement backprop in these things, is to draw the kind of pictures on the right side where we say we're unfolding the network. So we're considering the state of the network at every discrete time step. And now we see that the state at time t depends on two things. It depends on the current input, say xt, and the previous state st minus 1. So we can write an equation like the one above that says that the state at time t is a parameterized function. So f theta here is a parameterized function. We want to learn those parameters that combines information coming from the previous state and the current input. And of course, this kind of equation is very common when you study dynamical systems, whether it's for machine learning or other purposes. Now, one thing you have to realize is that you can also think about unfolding in an algebraic sense. So at the top, we have sort of the equivalent of the left-hand picture where we're thinking about how the state is updated at each time step. In the bottom equation where I wrote st equals gt of all the past sequence, we're kind of thinking about the unfolded computation, where this gt is just the function obtained by composing f over and over again. And so we see that the state at a particular time is a function of all the past. But if this is interesting from a machine learning point of view, because if you wanted to learn G directly, in other words, if you parameterize the learning system in terms of imagine G is some machine learning system that tries to predict the next state, the problem with this would be that you would need a different G for every length, right? For every position, you have a different G because it has a different number of inputs. And it would be hard to generalize to new lengths. Of course, with a recurrent net and parameterized dynamical system like on the top, you don't have this problem. You will naturally generalize to new lengths. And within even the same sequence, because we're sharing parameters across time, things you learn at a particular time are combined with things you learn at other times through the shared parameters. And so you basically have a very compact representation. Now, when you do that, of course, you're making some assumptions. You're assuming that the same kind of computation can be applied at every time step. And you may imagine cases where you really, depending on the value of t, you'd like to have a different computation. However, the good news is that if your state is rich enough, then you can always sort of emulate that kind of thing. So imagine that one of the components of the state is t. So you have, say, a unit that just increments by 1 at every time step. And so you can have t as a implicit argument, basically. And you can, if you have enough capacity in this f theta, you can basically emulate any gt. All right. So of course, once we regard the computation through this unfolded graph, it's very easy to apply all the things we've heard about regarding backprop. It's just like a very special kind of architecture where instead of having inputs coming just on one side, they're coming one piece at a time and influencing the intermediate states. In the example here, notice that we have an input sequence and an output sequence, and both the input sequence and output sequence have the same length. So this is one of the special cases that people have applied recurrent nets for. This is, for example, when I was doing my thesis and I was doing phoneme recognition. Well, you have acoustic frames as the X's, and the O's were phoneme classes or things like that. Now, there is another kind of recurrent net architecture which is very important to understand and very commonly used these days. It's the kind in which the outputs also feed back as extra inputs. And furthermore, we can make a probabilistic interpretation of what is being computed as a directed graphical model that is fully connected in some sense and fully observable. So what do I mean here? Now think about the O's as the outputs at each time step as representing a probability distribution. For example, the probabilities for each of the symbols that X can take at each time step. And then what we're going to be doing is we're going to be able to use the recurrent net to generate a sequence. So the dotted arrows here in this figure mean that we're going to sample. When we use the recurrent net in its generative mode, it's going to be just free running. It's going to produce its own inputs. So at time t, it's going to produce a probability distribution over the random variable xt plus 1, given all the previous ones. And we're going to be able to draw a sample, for example, pick the next character, given the distribution represented by OT. So you can imagine OT being a softmax over all the symbol values. And we draw a particular symbol, and now that becomes the next input. Now, I talked about symbols, but the O's could be vectors, real vectors. It could be any kind of random variables. So what are we doing here when we train this with maximum likelihood is we're saying we're given a sequence x1 to xt, and we'd like that our network gives a high probability to that sequence. We can decompose the joint probability of the sequence x1 to xt as a product of conditionals. So that's what you see on the right-hand side of the equation on the top. And each conditional is of the form p of the next symbol or the next observation. It doesn't have to be symbol. Given all the previous ones. And of course, we multiply all these probabilities, and that's just the standard decomposition of a joint into a product of conditionals, where the order here is the temporal order that is usually a natural thing to consider for sequential data. And so the training objective will just be minus the log of the thing on the top, which means that it's the sum of negative log probabilities for these conditionals. So we are trying to predict the actually observed next symbol given all the previous symbols, and we maximize the probability of getting that thing right. So it's just like a classification problem at each time step. And of course, replace classification by regression if it's real valued or any other kind of types of random variable. So that's the sense in which a recurrent net can be thought about as a generative model. And if you think about it now in terms of graphical models, for those of you who know a bit about that way of thinking, what you see is that there are no latent variables, or at least no stochastic latent variables. You can think of the S's as very special kinds of latent variables, but they're deterministic functions of everything else. So the S's are deterministic functions of the previous S, of the previous X's through the equation we saw in the previous slides, right? So the ST here is a completely deterministic function of all the previous X's. And so you can actually think of this as in different ways from a graphical model point of view, but if we ignore the S's as latent variables because they are kind of deterministic, then it's a fully observed model where which means that we can just apply maximum likelihood in very simple ways and compute the tractable gradient, and everything is easy and simple, and we can model the joint distribution. You can also think of the S's as latent variables, but as I said, they're deterministic, and the role they play is to make the the graphical model both statistically and computationally more tractable. So what you notice is that through this equation that defines S in terms of the previous x's, you actually have a full dependency of all the previous x's conditioning the next one. So it's not a graphical model where we have removed any of the arcs. It's a fully connected, directed graphical model, right? So there's no assumption, no conditional independence assumption. You can model any distribution. However, in general, for a graphical model, you'd think that if you had this fully connected thing, it would be very expensive. The number of parameters could blow up, and the computation could blow up in terms of the length of the sequence. But because we have introduced these intermediate quantities, the s's, the states, actually the parameterization is compact. It's just the thetas for each time step, as well as the computation is cheap, right? The computation doesn't grow at each time step in terms of the length of the sequence. It's always the same cost. So this is a very kind of efficient parameterization of a joint distribution. All right, we can play all kinds of games with these recurrent nets, and first of all, of course, we can think of mapping different kinds of objects to different kinds of objects. Like, for example, we can, on the top right here, what we see is a recurrent net that reads a sequence and then outputs a vector. So you can go map a sequence to a vector, and sometimes you have applications where this is what you want. We've already seen the case of mapping a sequence to a sequence where the two sequences are aligned. This was one of the earlier pictures, and I guess it's the one on the right, the second one on the right. The third example, which I'm assuming that, the third example is vector to sequence. So here we can generate a sequence, so it's the same picture as we had just in the previous slide, where we can produce a sequence in a stochastic sense, right? We can sample from that sequence. But however, we're going to condition all of the transitions on some vector, right? So that's the, I don't know if you see my pointer here. Is there a pointer? No pointer. Anyways, the thing on the left-hand side here would be a conditioning variable that's going to influence every one of the transitions. So now you're basically modeling P of an output sequence given an input vector. And then the one in the bottom is a sequence-to-sequence case where the two sequences don't have to be the same length. They could be even of different types. And for example, this is a model that's being used early on for machine translation, where you have an input sequence and an output sequence. And so what happens here is that you have two parts to this. You have reading the input sequence. Now that creates a representation through a summary of the whole input sequence in the state. And then we're going to generate an output sequence using the same generative model, but it's now conditioned on the state that we got as a result of summarizing the input sequence. Any question about these things? All right, good. Now, I told you that we can train these recurrent nets by maximum likelihood. This is also called teacher forcing. This name came before people thought that we were actually doing maximum likelihood. And there's a good reason for this name. So let's try to see what's happening when we train in the maximum likelihood way. You can think of it like this. There are two kinds of computations that need to be considered when we train in this way. There's the kind of computation we're doing when we train, and the kind of computation that we do when we use the model to generate a sequence. All right, so whether it's conditional or not doesn't really matter. So what you see in the picture with there are two kinds of dotted. There's the dashed and dotted, right? So the dashed is what happens during training. So in other words, during training, we have targets for the outputs. In other words, we know what the ground truth next observation should be. So given the past ground truth, we're trying to predict the next element of the ground truth sequence. And so the thing that we're going to be feeding in as input for the next time step is that observed YT coming from the data. On the other hand, at test time, we're going to be of course, we don't have any ground truths. At test time, we're going to use the output of the model, the sample from the conditional distribution of the y given the current state. And so we have these two kinds of loops. Now, they could coincide, but they could also be different. And you could easily imagine a situation where they would be different when the kinds of sequences that the model has learned to generate isn't quite like the kinds of sequences in your training set. In fact, in general, this is going to be the case. We never have a perfect model, right? So if it was a perfect model, it would only generate sequences like those in the training set, but it's not going to be the case in practice. So there's going to be discrepancy between the kinds of data that's fed in as input, in other words, what the recurrent net sees as the conditioning input when it's training versus when it's being used to generate symbols. And that discrepancy is a kind of mismatch, which means that it could be that the network is essentially doing something completely weird and wrong when it's being used. So let me give you a sort of analogy to understand how badly it could be. So imagine that what the network is doing is learning to drive a car, which is today a very important application of deep learning. And so let's say that the way we train our network to drive a car is we have a human drive the car, and then we just tell the network to predict what's the next position of the driving direction given the observations and the past driving directions. And if the network learns to perfectly imitate the moves of the human, it might be fine. But let's say that it makes small mistakes, and at some point it actually gets the car slightly off of the center of the road, and it's now at a place where humans have never been, because humans know that you shouldn't be so close to the border. And now the car is seeing a kind of input that it has never seen. And maybe you're lucky and it generalizes well and goes back towards the middle, or maybe you're not lucky and it goes even more to the right and it goes out of the road, right? So the problem is that it's going to see input configurations when it's generating, when it's acting on itself, that may be very different from the ones it saw during training, because the human driver, of course, doesn't visit these bad states that you might see when the model is actually running by itself. So there's a history of machine learning approaches to try to deal with this. And a lot of it is inspired from similar issues happening in reinforcement learning. I'm not going to go in detail into these, but one of the recent ideas that is having some success is called scheduled sampling, and it bears relation to earlier work called CERN and Dagger. And the idea is we're going to be sort of trying to make the network see the kinds of inputs that it would generate itself during training, so that it knows to kind of go back to the right, the middle of the road, the kinds of things that the human would do, the teacher would do. So in other words, the idea is that instead of picking the ground truth as input when we train, with some probability we're going to pick the ground truth, and with some probability we're going to pick the sample coming from the output of the model. And it turns out that it's actually wrong to do that from a machine learning point of view, that this procedure doesn't actually learn the right thing. But it's reasonable to believe, and I don't have any proof of that, but it seems reasonable that if we make that probability of choosing one or the other gradually decrease towards zero, not in the sense that it ends up just listening to the ground truth, then you'd be okay, and it would have some kind of exposure to the kinds of things that the kinds of situations that it would see when it drives by itself. Right. So one interesting question, there's something wrong in this, and it would take some time to go and really understand it. But one way to think about it is, imagine that we run the network in its training using the ground truth, and then we let it run by itself for a few steps, right? So it's what we call open loop. So it just takes its output and feeds it as input, and it might go in a strange place, and in particular, the place where it goes might not the right answer for the state where it ends up might not be the one that you have in your ground truth sequence. So if you go back to the driving example, maybe the driver was staying straight in the middle, and if the car decided to go a bit to the right, now the right action would be to go back to the middle, but maybe because the ground truth was staying in the middle, it says, stay in the middle, or even go a bit to the right because he was gone a bit to the left. So these could be inconsistent targets that we're giving to this network. So the question is really, how should we train this? And one idea I had when I wrote those slides was that, well, we don't actually want to match the ground truth target a few steps later. What we want to do is to match the ground truth in distribution. And so maybe something like GAN, which you will hear about, and you've heard a little bit already about yesterday, might be a good way to deal with this problem. Okay, so let me talk more about some architecture variations. So up to now, I haven't really looked into how we structure the architecture of the neural net. But what you see on the left here is sort of the vanilla architecture that I've been talking about. We could think of, and several researchers and papers have proposed different ways of making this kind of architecture deeper for each time step. And so you can do that in various ways. So one of the first ways that was proposed, I believe, by Alex Graves is the one on the bottom left called stacking, where essentially we're going to decompose the state into different levels. So here we call one level the H's and the other the Z's, but you could imagine having many more levels. And typically people will have like 5, even 10 levels, like in normal deep nets. So now what happens is that for a given input xt, there will be like a deep network, a feed-forward, if you want, a recurrent net going up to all the layers of the recurrent net. But at each of these layers, like the HT, for example, it not only depends on the current input, but of course, and the previous layer, but also on the previous value of that level's state. Okay, so that's the stacking version. Another way that you could increase depth is to think about making the transition from one state to the next state deeper. Instead of having a single affine followed by nonlinearity for going from ST to ST plus 1, you could insert like an MLP, for example, like in the picture in the middle. And similarly, the mapping between state and outputs could be deeper, right? So you could, again, insert one or more hidden layers. Now, there's a problem with this that I should have put there's iClear 2004. So we had a paper about this. There's an issue when you insert an extra layer from T to T plus 1, is that it somehow makes training more difficult because the length of the sequences to be considered is now like doubled. And so we inserted the little skip connection here that goes directly from T minus 1 to T, as well as the, in addition to the extra nonlinearity, extra layer in between. That's connected to the problem of long-term dependencies, which I'll come to in a few minutes. You can also sort of think out of the box and expand the kinds of architectures from recurrent nets to other kinds of structures that are not really corresponding to a chain, right? So in the case of the recurrent net, you basically have the unfolded graph is basically a chain. But you could imagine other kinds of things. For example, you could have a tree, and these are called recursive networks. And they've been studied in the 90s and more recently by Richard Socher in a bunch of papers where he applied them to both natural language and images. Another kind of architecture is the bidirectional recurrent net. So this is the one on the top right, where you have two recurrent nets, one going from the past to the future, and one going from the future to the past. And then you think of the concatenation of the state at each time step as a representation for the whole sequence, right? Because if you think about it, the state in the, say, left-going RNN summarizes everything from the future at a particular point. And the state in the right-going RNN at the same time point summarizes everything from the past. So now if I concatenate these two states, I have a representation which contains information about the whole sequence. And this is true at every time step. So now what we have, if we take those two concatenated states and we do something with them, like we compute a new representation, is we have a representation, we have a feature extraction, which depends on the whole sequence at every time step. So we're extracting features at every time step, which basically will focus more on what's happening in the neighborhood of time step, but could be influenced by everything. So in other words, you can think of it like it's a context-dependent feature extraction. Like the normal feature extraction, we look at one time step or a fixed size window and we get some features. But now we have features that, of course, will tend to tell you more about what's happening in a particular place, but they will be sort of influenced by potentially everything, the whole sequence. Now, of course, one problem with this is we lost the causality. In other words, we can't, for example, we can't use this to generate the inputs because we would be using the future to generate itself, which doesn't make any sense. But we could use this as a pre-processing to extract information from a sequence. So when, for example, we're mapping a sequence to a sequence, or a sequence to anything else, this kind of architecture is very useful, and it has become even a standard for many applications. There's another kind of extension of recurrent nets, which is interesting, maybe less used as the bidirectional. I would say the bidirectional nets are the most commonly used these days. But another interesting direction is basically, everything that works for 1D can be extended to 2D or 3D pretty naturally, right? So instead of having a chain that goes left to right, you can imagine that you have, say, a 2D plane, and that's really useful for images, and we've done things with that, where at each position you now have a state. So at each ij position you have a state, and that state depends on the state at the one on the left, the state on the left, so at my I minus 1j, and the one above, so that's ij minus 1. So that creates a kind of grid where you can actually compute any state by traversing the grid in some reasonable order, like diagonals or something. And of course, you can then backprop and do everything that you want. So you can generalize this chain idea to 2D or 3D structures. Yeah, you can play with the parameterization. So one of the things we've done recently is instead of having the state being a defined function of the previous state and input, we can introduce some gating or multiplicative interactions. So this dot with a circle is just element-wise multiplication, or some more general form where you now introduce more multiplicative interactions, and somehow this can actually help to learn some things without increasing the number of parameters. So we see these gating or multiplicative types of computations being useful in many instances you'll see this week, and this is just one example. Okay, so now let me go to probably the most important part of my presentation, which is about the issue with training recurrent nets, and why, in particular, learning about long-term dependencies is difficult, is fundamentally difficult. So this is summarizing a paper that came out in '94, and I started working on this around 1990, and I'm going to tell you more about this. So in '91, when I was at MIT, I was trying to understand why my recurrent nets that I had used for speech recognition weren't learning those long-term dependencies. I really didn't have that concept clearly in my mind, but I was trying to understand, why is it that sometimes it doesn't learn? And so I tried to reduce the problem to a very simple case, which is a single neuron, okay? And a single neuron trying to learn to store one bit of information. I think you can't have simpler than that. And I found that even that really stupid simple task, the network would fail to learn it if it had to remember that piece of information for a long time, and I didn't tell it that it had to learn it until the end of the sequence. So the input would be something like this. So either the first input was large, or the first three inputs were large, or they were small, so it's a binary information. Then there was noise. And then only at the end of the sequence, I would tell the recurrent net what the right answer should be, which is basically output a 1 if the initial input was large, and output a 0 if the initial input was low. And if I train this with a target coming, soon after, so for a short sequence, like say 5 or 10 time steps, it would work fine. But if I went to like 20, 30, and like 50, now the probability of successfully learning the task went down to like 5% or something. It basically didn't work most of the time. And I was very surprised because this should have been a very easy task. So what was going on? So to understand what was going on, it's good to go back to basic notions about dynamical systems. Because if you think about that little situation, what we have is we have this dynamical system. We started in a particular place, so either with the input being large or the input being high, and so we want to keep that information. We want to remember in the state that the initial state was either in some region, so we start in the region corresponding to a high value, or we start in a region corresponding to a low value or corresponding to a high value, and then we follow the dynamics. So in the state space here, I imagine this is a 2D state space. Actually, in my example, it's a 1D state space. What happens is that the network will follow the dynamics, like follow some arrows. So you can imagine that every position you have arrows, and these arrows will tend to bring the system towards some regions. We call these regions attractors. And in particular, you can imagine the simple case where it's a fixed point attractor. So there's one place where it wants to go from anywhere you start. And the regions in which the dynamics would lead into the attractor are called the basins of attractions of these attractors. And so there is a boundary between those basins of attraction. If you start on one side of the boundary, you will tend to go to this attractor. If you start on the other side, you will tend to go to that attractor. Right, so there are a few interesting things here. First of all, from the point of view of the size of the gradients, there's something really funny happening around the boundary region, because if I move by epsilon, going from one side of the boundary to the other side of the boundary, the result at the end of the sequence will be very, very different. So the derivative of the state at the end of the sequence with respect to the state at the beginning of the sequence will blow up, right? In other words, a small change at the beginning becomes a huge change at the end. And of course, there are other cases where you have things like this with fractal dynamics and so on. But even in a simple case like this, you see that you might end up with very large derivatives. So these gradient explosion might happen in this case. There's another thing, which is that there's a property of these basins of attraction, is that inside the basin of attraction, and in particular near the attractor, the derivatives of the dynamics function, the function that maps state to next state, have a particular property that essentially the derivatives are less than 1. So derivative is less than 1 means that we say the map is contractive, meaning it takes two nearby points to 2 points that are even closer. So the map is either contractive or it's expanding, right? So if it's expanding, it means it takes 2 points and maps them slightly even further from each other. And actually in different directions, the answer might be different. Right, and that corresponds to the eigenvalues of the map. So of the Jacobian of the map. So if you think about that transformation from t to t plus 1 as a function, it has a Jacobian matrix, and that Jacobian matrix has single values or eigenvalues. Either way, the important question to ask about those eigenvalues is in magnitude, are they less than 1 or greater than 1? If they're less than 1, then somehow the dynamics will tend to be converging towards some place. If it's greater than 1, then it's pushing you away. So why is that important? Because in the region where the derivatives are less than 1, then you are in a place where you're contracting and noise will be cancelled. So if you are in such a region and you have a bit of noise being added to your state, the system will be robust to that noise, and you will still be able to converge to the fixed point. If you're in the expanding region, then a bit of noise will be blown up, and eventually you can go out of the extractor and forget the bit, right? So, because forgetting here means going from the basin corresponding to, say, 1 bit to another one. Basically, you've lost that information. So the thing that really matters here is whether those derivatives are less than 1 or greater than 1. And if we want to store information reliably, in other words, we don't want to be kicked out by a little bit of noise from that information we stored, like the 1 or the 0 that I had in my example, then we want to make sure that the dynamics stays in the regions where the derivatives are less than 1. So why is that a problem? It's a problem because if you look at the gradients that we would use, for example, for backprop, they involve asking the question, how does state at time t influence the final loss? So you can think of the final loss as a function of all the previous states, and each state depends on the previous state and so on. And because of this decomposition, we have a composition of functions, and by the chain rule, we can write this gradient as a product of these Jacobians at each time step times one final gradient vector for the relationship between the state at the end of the sequence and the loss. So what we have here is a product of matrices and a vector. So now each of these matrices, if they have eigenvalues of the Jacobians that are less than 1, what does it mean? It means we're basically multiplying a bunch of numbers that are less than 1 together. And if you multiply many numbers that are less than 1 together, what you get is vanishing gradients. So this actually was independently discovered by Sepp Hochreiter, and he wrote about it in his thesis in 1991 in German, so I didn't really know about it until a few years later. And this is actually interesting. I learned this recently. Not only he discovered this issue that the derivatives of the state in the past versus the future, are obtained as a product of these Jacobians, and if these Jacobians are small, then you have vanishing. But this also actually led him to come up with the LSTM, which I'll tell you about later. And he started thinking about LSTM in his 1991 thesis. The actual LSTM paper only came up in 97. I'll tell you more about it. Okay, so why is it that having these derivatives converge to 0 as we consider longer sequences, why is that a problem? Because it's gonna mess up our parameter gradient. So the equation I'm showing here is not the way that the gradient is computed by backprop, but you can rewrite the gradient equations in this way to understand how it's composed. And you can rewrite the gradient of the costs at some time in the future, like the end of the sequence, with respect to parameters as a sum over all the previous time steps. So we have the final time steps t, and now we consider the sum over all the previous time steps tau, where we're going to consider that the way that the parameters influence the costs at t at the end of the sequence is that the parameters are going to influence the state at tau, some intermediate time. Then the state at tau is going to influence the state at t much later, and then the state at t influences the costs. All right? And now we have a problem with this middle quantity here, d state at end, d state at some intermediate point. And the problem is that if we want to be in the region of the state space and the parameter space that allows to store bits of information reliably, we need those derivatives to be less than 1. We need those eigenvalues to be we need the spectral radius to be less than 1. We need all the eigenvalues to be less than 1, because this is the condition that will allow to store information reliably. But at the same time, this condition makes it so that this derivative, this matrix, which is a product of all the intermediate Jacobian matrices, converges to 0 exponentially fast in terms of the length of the sequence. So why is that a problem? Because now we have this sum. Some of the terms will be very small because they are exponentially smaller than the other ones. So the terms that regard long-term dependencies, so in other words, how the state in the remote past, some far in the past tau, influences the current t, those terms will be very small compared to the terms in that sum corresponding to what's happening when tau is very close to t, right? So what's happening is that the total gradient is a sum of terms, some of which will be much smaller. And we know what happens numerically when you add a large number and a small number. Basically, the small number loses. You lose that information. I mean, if you, and especially if you think about stochastic gradient descent, there's kind of noise happening in this gradient. And so what we're going to have is essentially that the long-term dependencies are going to dominate. It's going to be easy for the network to learn the short-term dependencies, but it's going to take forever for the network to learn the long-term dependencies. And forever could be really bad in some cases. All right, so this is really, really important. And I want to make a pause here to allow you to ask questions. Yes?
This might be really crazy, but could not just rescale?
I tried it.
And what happened?
Didn't work. But the problem with rescaling is that then you don't have any guarantee that is the correct gradient anymore. So if you're lucky, maybe all of those terms have the same sign, for example, and then it would be fine. But let's say some are positive, some are negative. You change the weighting of each of them, and now you might go in the wrong direction. Yeah?
It seems that fundamentally you have a problem because you have a fine timescale, but you don't have sort of coarser timescale which do opposite.
Yes, I'll come to that as one of the directions to try to solve this problem. But note that it won't solve it completely. It would make it easier because we're trying to reach between a tau and at through some steps that are somehow less nonlinear and have less Jacobians closer to 1, basically. But that's a very important direction of investigation.
You said that it might take forever for the network to learn these long-term dependencies. So are you saying that in the limit of infinite time it will eventually learn them?
I think so, yeah. I don't have any math to support this thing, but intuitively it's just a matter that the total gradient is now, has important terms from a statistical point of view, but then numerically these terms are very, very small, right? So in principle, you would first kill off you would learn the short-term dependencies, and then those terms would be small, and then eventually you should be able to learn the long-term ones. But in practice, because you also have noise in the gradient coming from the fact that you're doing SGD, and all kinds of imperfections, or even numerical precision issues, it becomes harder and harder. Yes?
How complicated the dynamics can be? In terms of, can the attractor be of measuring on zero?
Sure.
That's a very complicated thing.
Yeah, but really here the argument I made doesn't really care about the shape of the attractor. It only depends on the fact that for it to be an attractor, the eigenvalues need to be less than 1 around it.
So you cannot get closer and closer to the attractor, but you do not care.
No, but I don't care where I'm on the attractor.
Because it's a solution. It's going to be a
Yes. Okay. So in general, when you store many bits, you're exactly going to be in that situation where the attractor isn't a point, right? Otherwise, you would need one attractor for each value that you want to store. It's much more efficient to have kind of a distributed representation where the attractor is actually a multidimensional object, and now you can store many bits sort of in a componential way. But anyways, it doesn't matter. The point is, to store information reliably, you need these contractive mappings, but contractive mappings equals hard to learn the longer term dependencies. Yeah?
And Is there another problem is where you start the initial conditions will be the point on the boundaries of the...
Yes, that could be a problem too. And in practice, when we train recurrent nets, we see this happening. So rarely... no, not necessarily. I mean, that would be one instance, but simply the fact that you go in those places where the eigenvalues, in some regions, the eigenvalues are larger than 1. And if you spend time there, you're going to receive some very large gradients, and that can simply throw off your learning. In fact, that's one of the common problems with training RNNs. But the good news is that we have a trick to fix that, which I'm going to explain in a couple of minutes. Yes?
What about second order approaches? So
yes, I tried that too. Yeah. And we had some hope for a time that it could solve the problem, but it's not it. It could help in some cases, but it doesn't seem to be a general cure. Yes? So just before that, the reason why we thought this could work, and this is really ideas coming from Ilya Sutskever and James Martins, is that if we're lucky, when the components of the first derivatives, so these are components of the gradient. So you can think about components also of the second derivatives. So if we're lucky, the components of the second derivatives also scale in the same way. And then when you multiply by the inverse Hessian, that kind of cancels this issue. So there's hope, but it doesn't always work, and I don't really understand why. All right, I should probably move on to get a chance to see the rest of the material. Last question.
Do you think residual network kind of solved this problem?
What networks? I didn't hear.
Do you think residual network kind of solved this problem?
Well, residual networks are feed-forward networks, and you can think of residual. It's the other way around. Residual networks work because they do, like GRUs or LSTMs or highway networks. They have a Jacobian close to 1 because they have this. Next state equals previous state plus something. If the something is reasonably small, then the dominant term in the Jacobian is this identity. All right, I should move on. Okay, so yeah, it's interesting to point out, though, that the situation in the feed-forward case is not quite the same, although there are some really important parallels and lessons to be considered. So this is a recurrent case, and I've kind of drawn here, I put it upside down, and I've put in red the fact that the weights now are different at each layer. So in the recurrent case, we have inputs coming at each time step, but that's not the main thing. The main thing is that the weights are different at each time step. And so that makes a huge difference because basically especially if the target only comes at the end. Now, in principle, you could do the reweighting. I forgot who proposed we should do a reweighting. Well, here you can do a reweighting because there are, you're not adding up these things. Now, forget about the sum. They all go to a different layer, right? So you have a different set of weights for each time step, for each layer. So now you can reweight. And in fact, it's a good thing to do it. And I think the adaptive learning rate methods do something like this. Unfortunately, reweighting the layers in a deep net, although it can help, doesn't necessarily completely solve the problems of learning deep nets. But it's something to keep in mind. All right. So I guess I said all these things. Let me probably skip this. Let me tell you about the clipping. So there's a very simple recipe to get rid of the problem of the large eigenvalues. So when the gradients become very large, because you multiply numbers that are greater than 1 together, you get a kind of explosion. And the recipe is basically when the gradient is large, don't trust it. Very simple, right? Because if you were to take your current parameter values and add this huge gradient, it would just throw you off very far from where you should be. One thing to keep in mind and why this makes sense is that the gradient descent algorithms make sense when you make small steps. If you have a huge gradient and you add that with your current learning rate and you make a big step, you could go anywhere. It's going to be, it's likely to be wrong. So in particular, you have to think about the most important information about the gradient is the direction it tells you to go. But the magnitude could be completely wrong, right? So what we did is we take the gradient on the parameters and we check. If its norm is greater than threshold, we change the norm so that it's equal to the threshold. So it's very easy. It's a one line to change in your code, and it prevents the issues you have with gradient explosion. Now let me tell you about the picture in the bottom. People used to think that the main optimization sort of landscape to keep in mind when we train neural nets or other kinds of problems actually is that there's a conditioning problem, and there is a conditioning problem, meaning that, so this is supposed to be the error or the cost with respect to the parameter space on the plane, meaning that you have directions where the second derivatives of the cost are very large, and directions where the second derivatives of the cost are very small, and this is slowing down training and so on. But in recurrent nets, actually you might see things like this. This is actually the case with a single neuron with a feedback. And you have these ridges. So instead of these valleys being symmetric, you have very high derivatives on one side, but not necessarily high derivatives on the other side. And here you have a nice slope going down in this direction, so you actually would like to go down in this direction. The problem is, as you do that, you approach this region, which is close to probably a boundary of basin of attraction. I mean, it's not. This is in parameter space, so it makes it possible to approach those boundaries that have very large gradients. And near those boundaries, the gradient become huge, and they kick you off and throw off the learning. So by simply rescaling the gradient, or sometimes just ignoring it and doing a random move, you just go not too far away and then continue, and that really solves a lot of these problems. It doesn't solve the long-term dependencies problem, but it solves the problem coming from the large gradients. So this is called gradient clipping, and it's very, very efficient. And you should all have it in your RNN code. All right. So now I'm going to tell you about approaches to try to deal with this problem of long-term dependencies. So in the 93 paper that we wrote about the long-term dependencies, so this was an early version of the journal paper in 94, we proposed something that has the flavor of LSTMs. It's not the same thing, but the idea was that, again, we have this memory cell that at each state gets updated by just copying itself, and we have some kind of decision that gates that whether we copy or we don't, and we use some kind of heuristic to decide how to propagate gradients. But this idea that you should have this kind of self loop to keep information for a long time was there, and it was also in 91 in Sepp Schreider's thesis. So actually, let me tell you about LSTM right now. So there are different variants of the LSTM, but basically all of them, the central idea is there's this state variable has a self loop with itself. In other words, they call it the cell in the LSTM. The new state will be equal to the old state plus some kind of update. And we can control with a gate whether we actually copy the old state into the new state and whether we actually have an update coming. So the important one is the forget gate here, which multiplies the self loop path, and so it can kill off the self loop path. And the reason you want to do that is that if you didn't have that, then it would just keep adding and adding, and the state would keep growing and growing. This might prevent you from forgetting things. Sometimes you actually want to forget things because you have limited memory. And in the case of LSTM, there are also extra gates which control whether we actually add something into the state. So there is the input, but there's also a gate which multiplies this so it can kill off the thing that will be added. And they also have an output gate, which I think is useless, but controls whether something is going to be sent to the outside world. And the GRU, gated recurrent unit, has a slightly simpler architecture, so it has the same self loop, and it works basically the same, and it's a bit cheaper to compute, so several papers are using it, but it's kind of the same principle. So that was 97, the LSTM. In 95, we there's another paper that's missing. I should have. We proposed in NIPS 95. We proposed to use temporal hierarchy. So this is answering Doina's suggestion that maybe we could use multiple levels of timescales in order to bypass this problem of having the multiplication by many Jacobians. So what I mean here is, here in the bottom you have a regular recurrent net, but at the next layer you have a recurrent net that's updated less often somehow. And then another one even less often. So here I double the period. And so what happens is that even though the path through the fine timescale recurrent net may just make it impossible to learn long-term dependencies, you could learn long-term dependencies by having gradients propagate through the shorter path that goes through the slow timescale. So this is the general idea, and the devil is in the detail. Like, how do we define when those upper ones should be updated and so on. You don't even have to have discrete updates. You could have slowly changing units higher up, rather than I update every 10 time steps. I just update by copying my old value a little bit and adding a little bit of the new value. Another idea which came at about the same time from Lee Giles, in the top right, what you see is you can have recurrent nets with skip connections over time. So again, what you're doing is now you create those paths in the graph which allow to go sort of faster from the past to the future with less nonlinearities in between, and that also works. So an example of these hierarchies in recent work we did with Julian Serban and others here at Mila involves two-level hierarchy, where there's one level of recurrent nets that is reading, say, words in a sentence, but you could also imagine, say, characters in a word, and another level which is working at the level here of sentences, and you can have more levels if you wanted. But you can imagine many ways that you can implement these ideas of a hierarchy. Now if we go to something very recent, which I think brings fresh ideas to this question of long-term dependencies, memory networks, which you will hear more about. You can think of memory networks as some kind of recurrent network where the state, part of the state, is now stored in a big memory, a big outside memory. I'm going to show you the next picture because it's kind of easier to understand. So you have a set of memory cells, and at each time step, what happens is that those memory cells either get copied from the previous time step, or somebody writes something into a cell. And somebody is a neural net, right? A recurrent net. And when you write something into a cell, of course, you're going to be forgetting old values. But most of the time, if you have a big memory, and you're only writing at one place at a time, basically, you're just copying. And so information gets propagated for a very long time. In other words, if you have like a memory, like a memory of a Turing machine, when you store things in there, it robustly stays for a long time, right? And so that kind of sidesteps the problem of long-term dependencies, or at least it reduces it considerably. So there's a nice recent paper from Mila and also involving Toronto people, where we try to think of how to characterize these recurrent net architectures, and we came up with 3 interesting measures to help us understand an architecture. So one of them is the feed-forward depth. So that's like the yellow path. So remember, if we stack a recurrent net, so how long does it take to go from input to output through different layers? That's basically like going in the feed-forward direction. Then you have the recurrent depth, which tells us what's the longest path from a particular time step to later in the future, potentially going through all the complications of the architecture. And in this particular architecture, you see that you can pack 2 nonlinearities for each time step, because you can go through this layer, then the one above, and then at the same time step, and then go to the next time step at the same level. And so this red path here actually packs twice as much depth per time step than a standard architecture. And then the third quantity that's interesting to consider is the skip coefficient, which tells us about, that's the blue arrows, that tells us not about the longest path from the beginning to the end, but the shortest path. And that's also useful, right? You want to have these short paths in order to learn long-term dependencies. So there are experiments that I don't have time to tell you about showing how all of these things can matter. Briefly, there's been a bunch of work exploring how we can play with the weight matrix in order to make it easier to learn long-term dependencies. So for example, you could initialize it to be orthogonal, or you can actually constrain it to be a unitary matrix, which has all the eigenvalues equal to 1. Or you can play a game similar to what you have in stochastics and ResNets, where sometimes the Jacobian is just the identity because you just copy the previous state to the next state. And you can randomly do that, and this is called zone out, a recent paper also from Mila. Okay. Now, earlier I said that in a standard recurrent net, we can interpret the computation and the model as a directed graphical model without any latent variables. And what that means is that all of the randomness that is injected when we generate something is happening at the level of the observations, at the visible variables, at the data level, right? So if we're working on pixels, it's like the way that we generate an image is that we randomly pick the next pixel and then the next pixel given the previous pixels. But it would make a lot of sense if instead the randomness was about taking decisions regarding not the low level, not the pixels, but the high level in the hierarchy. Like, what is this picture going to be about? What is this text going to be about? What is this music going to be about? You'd like to take these high-level decisions and then condition on these high-level decisions, you might want to put in the details at the low level. So for this, you need to introduce actual latent variables, not just the deterministic ones we have in a regular recurrent net. We need to introduce these latent variables at sort of a high level of the hierarchy corresponding to high-level abstractions. So it's like you decide on the high-level structure, and then given that, you may decide low-level structure. So at the last NIPS, we had a paper about combining ideas from what's called variational autoencoders, which hopefully will be also covered later this week in recurrent nets. Since you haven't seen these things yet, I'm not going to go in much detail and I don't have much time. But basically, you can combine the ideas in some of these modern latent variable models in recurrent nets, and you can stick in high-level random decisions in the computational graph in the model. And so the model I showed you earlier, which has 2 levels of recurrent nets, like one working on words, the other working on sentences. You can also have random variables at each time step which control sort of high-level decisions about, maybe what topic are we going to be talking about in the next sentence, given everything that we've said before. And then, given that, we can generate the next sentence. And so that's also been work of Julian Serban. So there are other fully observed neural nets that are directed graphical models that are not really recurrent nets, or maybe different from recurrent nets, and it's worth talking about now. And they belong to a larger family which uses the same decomposition I told you at the beginning. Remember, I told you that we can take a joint distribution P of x1 to xt, and we can write it as a product of conditionals. So that's one of the basic, things you should know about probability distributions. And so in general, we get a graphical model like the one on the right, where you see each variable like x3 being conditioned on all the previous ones. So these kinds of decompositions had been used before in the 90s. In particular, Brendan Frey, who's at Toronto, in his thesis in 97, proposed a model that essentially has a logistic regression of each bit in a vector, given the previous bits according to some order. So we're now not talking about sequences, so there's no natural order, but we can still pick an order and then say we're going to model the conditional distribution of the ith variable given the ones from 1 to I minus 1. And we can just do a linear regression or a logistic regression to obtain those conditional probabilities. In 99, with my brother Sami, we sort of extended this to a neural net, where we said, okay, so those conditional probabilities, instead of being computed by a linear model, we're going to be using a neural net. But instead of having a different neural net for each conditional probability, now because we have these hidden units, we can share the representations that we've learned for other earlier predictions in coming up with the next prediction. So this is very different from a normal recurrent net, because in the normal recurrent net, there is this kind of translation invariance. In other words, we're assuming that the parameters that are good to predict the next time step are also good to predict the one after and the one after. It doesn't matter. We can take the data and translate it, and the properties of those conditional distributions remain the same. But here, the pixels could be, the x1, x2, x3 could be anything, like any random variable. There's no equivalent of I can translate and keep the semantics. So the parameters of the conditionals, for predicting the third one would be different from the ones for predicting the fourth one. Now here we have the same thing, but we can share, because when we make, say, the prediction for x3, given x1 and x2, we extract some intermediate features that are hidden units. And we could use these to predict x4. Well, there should be an arrow here going from h2 to p of x4. A little bit later, in 2011, Hugo, whom you've heard on Monday, came up with a variation on this idea, which makes the computation very efficient, and also the statistical representation more efficient. So there's less parameters, by introducing a form of sharing that we didn't have. So the idea here is that the weights that go from x1 to a first group of hidden units will be the same as those that go from x1 to another group of hidden units corresponding to the prediction you want to make in the future. And so in this way, you have less parameters, and you can also organize computations so that it's actually more efficient by reusing the computation that you've already made for the earlier time steps. And you just have to add the new terms when you consider the next prediction. Say, I now consider x3 as an extra input. I don't need to redo the additions corresponding to the previous ones. I just consider the new input and add an extra term to the sum. So computation can be very efficient. Now, very efficient compared to the previous models, but it's still very inefficient on like a GPU, because they're still very, very sequential. For each input and for each output, we have to do a little bit of computation. So it's kind of harder to parallelize, but these kinds of models actually work quite well. And recently, people have been using this style of model on images, and they're called pixel RNNs. And basically, and these work surprisingly well. So it's kind of disappointing for people like me who've been working on generative models with latent variables, that these graphical models without any latent variables, so it's just like a big recurrent net essentially, with a particular structure, can generate the next pixel given the previously generated pixels. So you can organize what's previously generated in various ways. For example, on the top left, you see you just traverse all the rows, and then you predict the next pixel given everything you've seen before. Or maybe you can organize computation using this kind of triangle where you use only information from the top, or like the one on the right. I mean, there are various architectures that you could use, but the point is we define a sequence, and we have a little recurrent net which summarizes information you've seen in the past of the sequence and is used to predict the next pixel. And it's very slow because you have to go through all the pixels one at a time, which is very sequential, in order to generate, and also when you train. But it gives pretty nice images when you generate. It tends to get the local details very good, much better than the kind of deep generative models that have been there before, and you will hear about more later. So it tends to get texture quite well, and you can get pretty sharp and realistic images, at least on the scale that's been done up to now.
One question: Do you think the reason the global structure is captured correctly has to do with long-term memory, or is it just that there's not enough information in the data set to learn the global structure?
Oh, I think there is enough information. I think you can interpret the fact that it's not getting global structure as well as other models by thinking of the issue as one of long-term dependencies, but you can also think of it like it would be so much more convenient if you first decide like what kind of object is going to be in the image. And then your global structure would be decided, and then you fill out the details. Right? So ideally you want to have the two things. You want to have the ability to decide on the global structure in a kind of hierarchical way, but you also need to fill out the details so that the local texture and local coherence is well preserved. Other questions? Okay. Now, let me tell you about a last subject, which is a very old subject, which I think is coming back. There's an issue with backpropagation through time. Actually, there are several issues. For those people who care to think about how brains might implement some machine learning algorithms, one issue with backprop through time is that it requires a form of computation that seems a bit crazy. You have to go through the whole history, and in worst case, that means you have to go through your whole life, and then store everything, every state of your brain, somewhere, and then replay it backwards, and fix things using gradient steps, and then relive your life. Okay, better. Okay, I'm maybe exaggerating. Maybe you could get away with only learning about the dependencies across a single day, but then you'd think that something is missing. And maybe at night we're replaying backwards the things that are happening during the day. There's some clues suggesting something like this may be happening, but it seems a bit crazy. And also there's the issue of having to store the full sequence of states, because you need to store that somewhere. So it's like you have your main state, but you have a memory which isn't part of your state, which is used as a control, part of the control algorithm where you would store these things. It's not inconceivable for brains, but again, it seems a bit of a stretch. So it would be nice if there were other options. Also, from a purely AI machine learning point of view, when we start playing with very long sequences and large recurrent nets, the memory becomes a real bottleneck. For example, we've been playing with acoustic signals where, say you have 16,000 acoustic samples per second, yes? And so the number of time steps grows very fast. So if you want to do 10 seconds of audio, that's a lot of time steps. And you have to store the state of recurrent net for every one of those time steps. So that just not going to fit on your GPU, for now at least. So that raises the question, are there any other ways to train recurrent nets besides backprop through time? And the answer to this has already been given to some extent in a 1989 paper from Williams and Sibser. In fact, the idea is much older, and people doing automatic differentiation much before that had already solved the problem. And so the idea is that we can compute the gradient in a forward way rather than in a backward way. And to see why this is possible, let me use a blackboard. It also will help to understand why, for now, we don't have a good, efficient way of doing it. So remember, I told you that the total gradient, if you consider a sequence, like where only at the end we get a loss, and we've got now a Jacobian for the first time step, a Jacobian for the second time step, a Jacobian for the third time step, and so on. And then we have dl, ds, this is S0, S1, S2, S3, S4. So we've got dl, ds4, which is a vector, right? So if we want to compute, say, the gradients with respect to those weights, what we need is multiply dl, ds4 by ds4, ds3 times ds3, ds2, and so on, ds1, ds0. So we have a product of these matrices, and we have a vector on one end. Okay. So if you think about the computation that is being performed by backprop, what it does here is you start from the end, which gives you the gradient on the state at the last time step, and then you multiply that vector by the matrix corresponding to the Jacobian that goes from, relates S3 to S4. So we do a vector times matrix multiplication, and then we get a vector. And the cost of that operation is the size of that matrix. So it's, let's see, if we have n dimension, this is n squared. So we do this n squared vector matrix operation t times. But we have to do it backwards in time. But we could get the same result by going forward in time, by starting from this matrix, and then, by the way, here is this ds0 dw, because this is the w we care about. So we could start with this matrix, and then multiply it by this matrix, this matrix, this matrix, this matrix, and then this vector. How much would it cost? Well, now we've got a bunch of matrix multiplications. How much does it cost to multiply two matrices of n squared? It costs n cubed. So instead of doing n squared computation for each time step, now we need to do n cubed computation for each time step. In fact, it's worse than that, because that matrix here is not n squared. It's n times the number of weights, which is itself n squared. So this is an n by n squared matrix, and when we multiply by this n by n matrix, we get an n. The result of this is going to be an n by n squared again. And how many computations are we going to do? We're actually going to be doing n to the 4 computation, right? Because for each of the elements here, we're going to have to look at all n here. So the amount of computation we need here for this is order of n4, whereas previously we had order of n squared. Okay, that's really bad. But we could do it. In other words, we can compute the gradients by moving forward in time rather than backwards in time. We can do this even before we know what the right answer will be. And anytime we get a right answer anytime we get a loss, then we can use it to update the weights. I'm not doing the full decomposition here. I'm considering a very simple case where the loss is only at the end, but you can generalize it to the case where the loss is at any time step. But the point is, it's like multiplying matrices from right to left versus left to right. It gets you the same answer, but it's going to be a lot more expensive. Yes? It's exactly that. That's what I said earlier, that automatic differentiation people had discovered it well before. And so these guys realized, without knowing about automatic differentiation, you could do that, and you could thus compute gradients online in recurrent net. It means, as we are considering the next example, if we have kept a memory of, if we've kept a memory of dst dw, we can just update this and multiply it by, at any time, by the loss at t with respect to st, and that will give us the component of the gradient due to the loss at t, and we can make an update. In other words, that will tell us, this product will tell us how all the past states, the influence of the weights on all the past states is leading us to this particular loss, and how we should change the weights so that for this particular loss we make less of an error. And so we could just go forward online, as they called it. The problem is that it's just too expensive, and it's not even biologically plausible, because this means storing this matrix. This is it's a tensor, right? So for each neuron, you have to consider all the possible weights, not just the weights entering that neuron, but all the weights, right? That's the thing that's crazy. Now, there's some good news. Recently, Yann Olivier in France and his collaborators have come up with a method to approximate that matrix, D state D parameters. So this is a huge thing. You don't even want to store it. So they have a low rank representation of that tensor, which has the property that in expectation, so it's a stochastic estimator of that matrix. It's a low rank stochastic estimator, meaning that in expectation, it is the right value. And they have a random way of choosing things so that in average over these randomness, they get the right tensor. And it's never represented directly, it's represented as a product of two low rank matrices, right? So this idea that we might be able to actually do online learning in recurrent net is coming back, and might be something to watch for in the future. All right, I need to stop here and take any more questions you have.